This lesson discusses real zeros of polynomial functions. Now, there are two objectives for this particular part of our lesson on studying real zeros of polynomial functions. The first one is this: distinguish between rational and irrational zeros, and make sure you understand how to understand and apply the number of real zeros theorem. So there's a theorem, and the theorem discusses the number of real zeros that a polynomial function could have. It doesn't say will have, it says could have. Okay, so we're going to discuss that in a little while. Now, this lesson is very important you go through this lesson, because this lesson will lead to the next lesson, which discusses the rational zero theorem. And the rational zero theorem is an important theorem in the topics we're discussing right now dealing with polynomial functions. Okay, so in the first objective, make sure you understand what a rational number is and an irrational number is. So let's remind ourselves about rational and irrational numbers. So remember that a real number can be classified as a rational number or an irrational number. Okay, so a rational number or an irrational number. A rational number has this form. It has a form a divided by b, where a and b are integers. So a rational number is any number that can be written in the form a divided by b, where a and b are integers. A and B are integers, and in particular, remember, you can never divide by 0. So the only integer that b cannot be is 0, and b cannot equal 0. A can be 0, but b cannot be 0. Okay? And an irrational number, by definition, would be a number that's not a real number that's not rational. So we'll just define it like this: a real number not rational. So real quickly, some examples of rational numbers would be the fraction 4/5, because 4 and 5 are integers, right? Negative 2/3, because negative 2 is an integer. 3 is also an integer. The square root of 16. Square root of 16 is an integer, because the square root of 16 is 4. And I can write 4 as 4 divided by 1. And 4 and 1 are integers, right? And then don't forget your terminating decimals, like 0.75. That's a rational number, right? Because 0.75, if you read it correctly, that's 75 hundredths. And then 75 and 100 are integers. Okay? And then one other thing is that if you have, let's say, 0.6666 repeating, remember, so if you have a repeating decimal, that's also a rational number. A repeating decimal, all repeating decimals can be written as a rational number. In this case, this would be 2/3. Now, any number that's not rational, or any number that cannot be written as a fraction a divided by b, where a and b are integers and b is not equal to 0, would be considered irrational. So for example, the square root of 5. The square root of 5 is an irrational number. Square root of 16 is rational, because square root of 16 is a perfect square. And I can write 16 as 4 divided by 1, and both of those are integers. But the square root of 5 you cannot, because 5 is not a perfect square. So square root of 5 would be considered an irrational number. And then another one that you're probably more familiar with, or familiar with as well, is the number pi. So pi in geometry would be considered an irrational number also. That's why you can't write as a fraction. That's why we use a Greek letter. Okay? All right, so that was a quick summary of rational and irrational numbers. Okay, now let's talk about zeros. Let's remind ourselves about zeros. We learned about zeros before, but let's kind of review the idea of zeros again. Okay, so in example 1, it says this: find the zeros of the function 4x squared minus 9. Now remember what finding zeros means. So finding a zero of a function means this. So it means find the value of x for which f of x is equal to 0, for which the function is equal to 0. So in other words, my function is 4x squared minus 9. So the question is, where is 4x squared minus 9 equal to 0? And so notice we have a very simple quadratic equation. And so in fact, I can factor this. That's the difference of two squares. I don't have to use the quadratic formula. So I'm going to go ahead and factor this. And when I factor this, I'm going to get 2x minus 3 times 2x plus 3 equals 0. And notice that I have two factors whose product is 0, so by the zero factor property, I can set each factor equal to 0, because one of those must be 0. And so I end up with two linear equations, and so when I solve each of those linear equations, I get 3 halves, and this one would be negative 3 halves. So those are your zeros. So those are the two values of x that will make this function equal to 0. So the zeros are plus or minus 3 halves. And I'm going to list it as plus or minus 3 halves, or you can just say 3 halves, comma, negative 3 halves. But remember, plus or minus 3 halves means the same thing as 3 halves, comma, negative 3 halves. In particular, though, I want you to understand that these are real numbers, right? So these are real zeros. So these are real zeros. These are real zeros. And in particular, they are rational. And also rational real zeros. Okay? All right. So this particular function had two real zeros, and they were both rational. 3 halves is a rational number, and negative 3 halves is a rational number. All right. So let's look at example 2. One other thing before we go on that I want to mention about, remind you about zeros. So remember, zeros, if you were to graph this, zeros, so recall, zeros are also x-intercepts of the function. Okay, so it kind of makes sense, right? So it kind of makes sense that zeros are x-intercepts of a function, because the x-intercept is where the y value is 0. And then I let, remember, f of x same thing as y, so then I let y equal to 0. So those are the same thing as x-intercepts. I just want to remind you this because that's going to be important in a few lessons later. Okay, so let's look at example 2. Example 2. All right, so example 2 says this: find the zeros of the function x squared minus 2. So again, we're dealing with a quadratic function. And I'm using quadratic functions here because for this particular lesson, those are easier to deal with. All right, so remember, to find the zeros, we got to find, so in other words, to find the zeros, we need to let f of x equal 0. So solve that equation. So I'm going to set this function equal to 0. So x squared minus 2 equals 0. And notice that in this particular case, I have this quadratic equation, and I can solve this quadratic equation by using the square root property. All right, so I'm going to go ahead and bring the 2 to the other side, and so I get x squared equal 2. Now remember, when using the square root property, that's where you take the square root of both sides. So what I'm going to do now is I'm going to take the square root of both sides, but don't forget, when you take the square root, you get plus or minus. Don't forget the plus or minus. And so the square and the square root undo each other, so you get x to be plus or minus the square root of 2. And so those are your zeros. Those are the zeros. So those are the values of x that will make this function equal to 0. Now also remember, you can write this as two separate zeros, square root of 2, comma, negative square root of 2. In particular, though, notice those are real numbers, but they are irrational zeros. So these are irrational zeros. Okay, so those are irrational zeros. All right. Now, let's look at this theorem that I mentioned earlier. So the theorem I'm referring to is number 2. So understand and apply the number of real zeros theorem. Okay, so here's a theorem, and so we're just going to call it number of real zeros theorem. But basically it says this: if you have a polynomial function of degree n, where n is greater than or equal to 1, so you can have a linear function. If the degree is 2, you have a quadratic. If the degree is 3, you have cubic, and so on. But in particular, a polynomial function of degree n has at most n real zeros. It has at most n real zeros. Okay, it doesn't say it has exactly n real zeros, right? It says it has at most n real zeros. So if we go back to our first example, where the degree is 2, so the degree of this function is 2, right? So according to this theorem, this function has at most 2 real zeros. That's what this says, 2 real zeros. And in fact, notice it has exactly 2 real zeros. Okay, it cannot have 3, it cannot have 4, it can have at most 2. Okay, and so when we solved it, we found that it has exactly 2. And the same thing for our second example. So remember the second example, our second example was this one. So again, we had this quadratic function. It has degree 2. So according to the theorem, this function will have at most 2 real zeros. It may not have any. It could have 1, right? But it will have at most 2. It cannot have more than 2. And so when we solved this, we saw it has exactly 2 real zeros. They were irrational zeros, but they were still real zeros. Okay, so let's look at example 3. Example 3. Okay, so let's look at this problem. So it says find the zeros of f of x equal x squared plus 9. Now remember the theorem says that a polynomial function has at most, in this case, 2 real zeros. It may not have any, it may have 1, it may have 2, but it cannot have more than 2. The degree tells you at most how many it can have. Okay? Now let's go ahead and solve this. I want to show you, I want to remind you about something. You've dealt with this before in the previous course. But let me go ahead and find and remind you how to find the real zeros. So the zeros. So again, we're going to set this equal to 0, which means that I have x squared plus 9 equals 0. And just like the previous problem, I'm going to go ahead and use the square root property. And so I'm going to get x squared equal a negative 9. And then let me go ahead and rewrite this over. And then I'm going to take the square root of both sides, and I get plus or minus. What I want you to remember is this. So first of all, the square root of x squared is just x. And remember, the square root of a negative 1, remember that's not a real number, right? The square root of a negative 1 is an imaginary number. So that's where we define that to be I. Remember that? So these are not real numbers. So the square root of a negative 9 is not a real number. There is no number times itself that's a negative number. In fact, all numbers times itself is either positive or 0. It's never negative. All real numbers times itself is either positive or 0. It's never negative. So remember what this is. This is plus or minus 3i. So we have this complex number. So those are my real those are my zeros. They're not real numbers. So these are not real zeros. Okay, so remember these are complex zeros. Complex zeros. So you have that imaginary number I. All right, so remember this theorem. The theorem says you have at most 2 real zeros. In fact, this one didn't have any, right? This didn't have any. So the point I want to make again is that this theorem says a polynomial function of degree n has at most n real zeros. All right, so this one has at most 2 real zeros. When we solved it, we saw that it did not have any, none. They were not real. They were complex zeros. Okay? All right, so All right, so in example 4, so remember the degree here is 3. That's the largest exponent you see. The degree of this polynomial function is 3. So according to this theorem, this function has at most 3 real zeros. Okay? Has at most 3 real zeros. So this function has at most 3 real zeros. Okay? They can be, if they have any, if this function has any real zeros, and it does. It has at least one. We're going to talk about that in another lesson. But the fact that this is cubic, you're going to have at least one real zero, and we're going to talk about that in another lesson. But the theorem says you have at most 3 real zeros. Okay. In fact, and you're going to see how to do this in another lesson. But it turns out that the zeros of f of x are, and here are the zeros, -2, -1 plus 6i, and -1 minus 6i. Okay, so notice these are complex zeros. This is your only real zero, and it's actually a rational zero. So you only have one real zero. Okay, so remember the theorem says you have at most 3. You only have 1 here. And then these are your complex zeros. And there are 2 of them. So nodes of degree 3. Degree is 3. You have 3 solutions here. 3 solutions. 3 zeros. 1, 2, 3. This one is the only one that's real. The other 2 are complex zeros. Okay? All right, so that's going to take care of this lesson on our beginning discussion of real zeros of polynomial functions. Now, what we're about to do now is now that you know about what a rational zero is, what an irrational zero is, and also this theorem that says you have at most n real zeros if the degree is n, then we're going to now talk about the rational zero theorem. And so that's going to be the next lesson, the rational zero theorem.